Hello and welcome. This is Chapter 5, Section 1 on Trigonometric Identities, Part A. So our main goals today will be using reciprocal quotient and Pythagorean identities. So just as a reminder, our trig ratios. So let me zoom in here. So if you forgot, we create on a unit circle. Well, in this case, this isn't the unit circle. It could be any radius, but we will think of this as 1 in most cases. We create a reference triangle, and you just drop it to the x-axis, make a right angle. You have this angle theta here. This is our radius, and we have this as our x value. This is our y value. And you can do SOHCAHTOA, which is where you get all of these values. Just remember, you can't divide by 0. That's why you would have asymptotes at those places when we graph those. But we're going to be focused on using these for these next examples. So let's look at example 1. So we're going to be in quadrant 3. So if we notice, we have this. Quadrant 3 is down here. So we draw a lovely triangle, just a random triangle like this, and we put our theta here. Notice that we have the cosine, which is negative 7/8. Remember, we have C, A, S, and T, so both tan and cotangent are positive. Everything else is going to be negative. So this will be a negative value, and this will be a positive value when we find them. Now, what we have to do is enter in cosine. Cosine, if you forgot, is from the other side is our x divided by our r value. So we're going to be using those. So our x is 7. So we're going to put a 7 here. And we can actually put in a negative 7 if we like as like a coordinate. And this is our radius of 8. And then our y value will also be negative, which we can find using the Pythagorean theorem. So we can do like negative 7 squared plus y squared, let's put those as squares, is equal to 8 squared. And we can solve that to get that our y value is in fact the square root of 15 for this value here. And if we wanted to think about it, it will be negative because it'll be going downwards in a negative direction. So the distances are positive, but we'll consider this as negative and negative just so that we know when we divide those two, cotangent or tangent are positive, and cosine, sine, and their reciprocals are going to be negative. So now we just have to set up our two ratios. So cosecant of theta, if you wanted to remember, is your r divided by y value, and our cotangent of theta is going to be x divided by y. Now, all we have to do is substitute those values in. In this case, our radius was 8, and we found that the y value was a negative square root of 15. This is almost the answer we wanted. We just have to rationalize it by multiplying by square root of 15 over square root of 15 to get the radical out of the denominator. So now this is negative 8 square root of 15 all over 15 as our answer for the cosecant of theta. And it would be negative. Again, it would be in this quadrant. This one will be positive. This one will be negative. So if you didn't put those negatives in and kept them as lengths, that's fine. But this is just a good way to remind us of that as well. So now we take the x value, which was negative 7, divided by the y value, which is negative square root of 15, which you have two negatives now, which turns it positive. And again, we're multiplying by square root of 15 over square root of 15 to give us, this is positive 7 times the square root of 15 over 15 as that ratio there. So please try this one on your own. I will have an answer shortly, so check it on your own. So hopefully you tried it. I believe you should do Pythagorean theorem here. 49 plus 9, that's just 58, or square root of 58 here. Then you use SOHCAHTOA. Cosine is going to be 7 over square root of 58, rationalize, and then cosecant is going to be that negative square root of 58 over 3, or negative 3, whatever. Put the negative on there because it would have to be negative in this quadrant, because remember, cosine and its reciprocal secant are only positive. Everything else will be, in fact, negative. So these are our reciprocal identities. So it's just saying that, well, the cosecant of u and sine of u are reciprocals of each other. So In order to find the sine of u, I can just do 1 divided by the cosecant of u. So the main idea is this: if we look at this, the sine of u is the same as 1 over the 1 over sine of u, which is, that's the cosecant of u. So let's flip this so the sign goes back up top. Why would we use this? Well, the idea is if we have sine of u and we don't like it on the numerator, we can just move it to the bottom as cosecant of u. Or vice versa, if we have sine of u on the denominator and I don't want it on the bottom, I can move it to the top by just writing it as cosecant of u. The idea is we can get rid of fractions by using these identities and just moving them up or down from the numerator to the denominator by just writing them as their reciprocals. So then we have something called quotient identities, which we've already shown these. The quotient identities is saying, hey, well, if we know that cosine of theta is our x value on the unit circle and sine of theta is our y value on the unit circle, well, we could substitute in this here to have sine of theta on the numerator and then cosine on the denominator. So we get sine over cosine is the idea of tangent. Now we can just flip it over and have it as cosine over sine. So these quotient identities are very powerful because it says that, well, we can take tangent or cotangent and rewrite them as sines and cosines. One of our biggest things we do is rewrite things as sine or cosine because both secant, cosecant, tangent, and cotangent can be all changed into a sine or cosine. Therefore, we have things that we can use to manipulate and cancel or reduce things to 1 very easily. So here is an example of what we will be doing for this. So using algebra and the fundamental trigonometric identities, your answer should be a number or a single trig function. So we have to simplify this. So it's going to be like sine of x or cosine of x as an answer. So how do I do this? So I'm going to start rewriting things down. So this is going to be the cosine of x. And then the secant of x, I could rewrite that. Well, let's rewrite the bottom as tangent of x. But I could replace this with, or just move it down to the bottom by doing its reciprocal. So secant of x is the reciprocal of cosine of x. So I'm just going to rewrite that as cosine of x. And that is that reciprocal identity. We're just moving it down. So again, we could take this on the top and move it to the bottom by noting that the secant, let's rewrite that down. So if we have the secant of u, that is equal to 1 over the cosine of u, as we stated before. And if you look at your cheat sheet, that also has that. So it's like, hey, I'm just moving this to the bottom. Now, what's really nice about that, we could obviously reduce those, but let's first use a quotient identity. By the way, there are numerous ways to solve these. So this is cosine of x, and using the quotient identity, we can rewrite tangent as your sine of x over your cosine of x. And then you still have this cosine of x right here. But notice how this cosine is on the denominator now, and this cosine is on the numerator. One thing you should remember is this always is over 1. So a lot of people forget that. So just make sure that you have that there. Let me make it look like a 1. So here we go, back to a 1. There we go. So now what we can do is we can reduce those. So it makes it a little easier on your stuff. So now we're just going to use our algebra skills to reduce that into getting this is just cosine of x over sine of x. So we're just applying some algebra by reducing. Cosine over cosine is 1, or canceling out if you wanted to call it. And now we're going to use that quotient identity again, because cosine over sine is in fact equal to your cotangent of x. Now this is a single thing, and that's going back to your quotient identity. That cosine over sine is that cotangent of x, and that's all we had to do is get down to one single term. So let's do another example of this. So these can be done in a number of ways. So let's just start by, I don't know, let's put the secant of x here. What we can do, let's rewrite this as tangent of x. Let's just move this one to the top. Cosecant, the reciprocal of that is sine, so I can move that up to sine by that reciprocal identity. And now what I can do is now I can do the next thing is I can do secant and move that down to the below. So we could have done that all at once. So now I have the sine of x over tangent of x. And secant is cosine, so I'm going to put the cosine of x. Let's do that in a different color. So cosine of x again. So that is also the reciprocal identity, just to do that again. And then what we can do lastly here, well, almost lastly, is remember that this is sine of x, and then we can use that quotient identity. So we'll have the cosine of x here, and the tangent turns into sine of x over cosine of x, which is that quotient identity. And then notice that we can also use some algebra to reduce those. Let me move this up just a little bit. Oops, sorry. I needed to move this. And then what we have lastly is just, well, you have the sine of x and then the sine of x, which we can reduce just to a 1 here again, which is some more algebra. So we can reduce these, which is algebra, and then sine over sine. Sine over sine is just 1, which is some more algebra skills. So please try this one on your own. See if you can simplify it to one single term. Pause it. I'll have an answer shortly. So here is a way you can do it. I just rewrote the secant on the denominator as cosine, and then using reciprocal, then rewrote this as sine or cosine over sine using your quotient. And remember, when you're dividing by cosine, so this is all divided by this is dividing by 1, and you can flip this. So this flips to be 1 over cosine, and then we can reduce it using algebra, and we have 1 over sine, which then is just cosecant of x, simplifying using that reciprocal identity. So that's your last one, is a reciprocal identity.